Vought Aircraft Company Test Facility, Stratford, Connecticut. March 12th, 1943. The F4U Corsair sat on the tarmac like a caged predator, its distinctive gull wings and massive Pratt and Whitney R-2800 engine promising power that no one had yet managed to unleash. Chief Machinist Walter Simmons stood beside the aircraft, holding a set of modified propeller pitch specifications that every aeronautical engineer at Vought had dismissed as suicidal. The establishment believed one thing absolutely. Hamilton Standard's conservative pitch settings were the only safe configuration for the Corsair's brutal torque characteristics. Anything more aggressive would tear the reduction gearbox apart or flip the aircraft onto its back during takeoff. Then Simmons proposed his modification, a propeller pitch angle so steep that it violated every safety margin established by 3 years of careful testing. Senior engineers called it reckless disregard for pilot safety. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Test pilots warned that those settings would make the Corsair uncontrollable during carrier operations. Even factory workers whispered that Simmons had finally lost his mind after too many years breathing metal dust and hydraulic fluid. But on that first test flight, something extraordinary happened. The Corsair didn't just climb faster. It rocketed skyward at rates that shattered every assumption about what piston fighters could achieve. Radio operators stared at their instruments in disbelief as the aircraft punched through 15,000 feet in less than 4 minutes. The propeller pitch, everyone said would kill pilots, had just turned America's most troubled fighter into a vertical performance monster that would redefine close air support in the Pacific. The morning fog rolled thick across Long Island Sound as Walter Simmons entered the machine shop at Vought Aircraft on February 8, 1943. At 52, he was older than most of the engineers who designed the aircraft components he manufactured, but his hands understood metal in ways that no engineering degree could teach. 30 years of machining experience had given Simmons an intuitive grasp of mechanical systems that often surprised the young aeronautical engineers fresh from universities like MIT and Caltech. The F4U Corsair program was in crisis, and everyone at Vought knew it. The aircraft that was supposed to revolutionize carrier aviation had become a nightmare of developmental problems that threatened to end production before the fighter ever reached combat squadrons. Charles Lindbergh had test-flown the prototype in 1940 and called it the finest fighter aircraft he had ever encountered. But that promise had devolved into 2 years of persistent technical failures that made the Corsair too dangerous for carrier operations. The problems were systemic and deeply troubling to Navy procurement officers who had invested millions in the aircraft's development. The Corsair's long nose created visibility issues during carrier approaches that had already killed 3 test pilots. Its narrow landing gear track made the aircraft unstable during deck landings, with a tendency to bounce violently if pilots misjudged their touchdown point. Most critically, the massive R-2800 engine produced so much torque that inexperienced pilots struggled to control the aircraft during high-power operations, particularly during the critical transition from takeoff to initial climb. Commander Thomas Blackburn, assigned to evaluate the Corsair for operational deployment, had written a scathing report to the Bureau of Aeronautics in January. The F4U possesses exceptional speed and firepower, but its handling characteristics make it unsuitable for carrier operations without fundamental redesign. Recommend restricting deployment to land-based Marine Corps squadrons, where longer runways and reduced operational pressures can accommodate the aircraft's limitations. The assessment had devastated morale at Vought, where thousands of workers had dedicated themselves to building what they believed would be the Navy's premier fighter. More practically, it threatened production contracts that kept the factory operating and the workforce employed. Simmons had been following the Corsair program with the careful attention of a craftsman who understood that small details often determined whether complex machines succeeded or failed. His responsibilities at Vought involved manufacturing precision components for propeller pitch control mechanisms, the hydraulic systems that adjusted blade angles, to optimize performance across different flight conditions. Hamilton Standard supplied the basic propeller assemblies, but Vaught's machinists manufactured the mounting hardware and control linkages that integrated propellers with the Corsair's massive engine. The breakthrough that would reshape the Corsair program emerged not from engineering calculations, but from careful observation of how the aircraft actually behaved during flight operations. Simmons had spent weeks watching test flights from his position near the runway, noting how Corsairs struggled during initial climb-out despite their powerful engines. The aircraft seemed to wallow in ground effect, requiring excessive runway distance before achieving safe climbing speed. More troubling, pilots reported that the Corsair felt sluggish during combat climb maneuvers, particularly at the critical altitudes between sea level and 10,000 feet, where most Pacific air combat occurred. The problem, Simmons believed, was the propeller pitch settings that Hamilton Standard had specified for the Corsair installation. Those settings had been carefully calculated to provide safe margins during all phases of flight, emphasizing controllability over absolute performance. But Simmons suspected that the conservative approach was actually creating the handling problems that made the Corsair dangerous. By setting the propeller pitch too shallow, Hamilton Standard's engineers had created a configuration where the massive A2800 engine produced excess power that manifested as torque rather than thrust. That unused power was what caused the aircraft to yaw violently during takeoff and made it difficult to control during high-power climbs. Simmons's solution violated every principle of conservative engineering that had guided aircraft development since the Wright brothers. He proposed increasing the propeller pitch angle by nearly 8 degrees beyond Hamilton Standard specifications, creating a configuration that would force the engine to work harder during all phases of flight. The steeper pitch would convert more of the A2800's power into forward thrust, rather than rotational torque, potentially solving the controllability issues while simultaneously improving climb performance. The reaction from Vaught's engineering department was immediate and uniformly negative. Rex Beisel, the brilliant designer who had created the Corsair's distinctive gull wing configuration, examined Simmons's calculations with growing alarm. "Walter," he said carefully, as if explaining basic physics to a child, "propeller pitch isn't something you can just adjust based on intuition. We have 3 years of test data showing that current settings provide optimal balance between performance and safety. Your proposed modification would overload the reduction gearbox and potentially cause catastrophic mechanical failure." The criticism extended beyond Vaught's internal engineering staff. When Hamilton Standard's technical representatives learned of Simmons's proposal during a routine liaison visit, their response bordered on outrage. Arthur Holbrook, Hamilton Standard's chief propeller engineer, spent an entire afternoon explaining to Vought management why increased pitch angles would destroy the careful balance that made modern propeller systems reliable. "The Corsair already produces more torque than any carrier fighter in history," Holbrook argued, his frustration evident. "Increasing pitch angles will only make the aircraft more dangerous, not less. I cannot recommend this modification under any circumstances." But Simmons had found an unexpected ally in Lieutenant Commander John Blackburn, whose critical report had nearly killed the Corsair program. Blackburn understood that conventional solutions had failed to solve the Corsair's problems, and unconventional approaches deserved consideration, even if they contradicted established engineering wisdom. During a meeting in Beisel's office on February 22nd, Blackburn made a pragmatic observation that shifted the debate. "Gentlemen, we can continue following Hamilton Standard's recommendations and accept that the Corsair will never operate from carriers, or we can acknowledge that our current approach isn't working and try something different. What's the worst that could happen? We prove Simmons wrong and continue looking for other solutions." The first test installation took place in early March, using a standard F4U Corsair that had been pulled from the production line for experimental modifications. Simmons worked personally on the propeller pitch adjustment mechanism, carefully machining new control linkages that would allow the steeper blade angles he believed would transform the aircraft's performance. The work required precision that pushed the limits of Vaught's machine shop capabilities, with tolerances measured in thousandths of an inch and adjustments that had to account for the massive forces that would stress every component during high-power operations. Chief Test Pilot Boone Guyton approached the modified Corsair on the morning of March 12th, with the professional caution that had kept him alive through hundreds of experimental flights. The tall, rangy Texan had been flying for Vought since 1941 and had survived 3 emergency landings when experimental modifications had failed catastrophically. As he conducted his pre-flight inspection, Guyton paid particular attention to the propeller hub assembly, looking for any signs of improper installation or mechanical weakness that might cause problems during flight. The aircraft looked identical to every other Corsair on the flight line, its dark blue paint and white national insignia showing the wear of intensive test operations. Only the propeller blades themselves revealed the modification Simmons had made, their angle noticeably steeper than standard installations. Guyton reached up to touch one blade, feeling the resistance as he tried to rotate it manually. The pitch was definitely aggressive, forcing each blade to take bigger bites of air with every revolution. "She's set pretty steep, Walter," Guyton commented, as Simmons arrived to observe the pre-flight inspection. "You sure this isn't going to tear the gearbox apart?" Simmons nodded confidently, though privately he understood that his modification represented educated speculation rather than engineering certainty. The reduction gearbox is rated for loads well beyond what we'll generate, even at maximum power. The real question is whether the handling characteristics improve or get worse. The engine start procedure revealed the first hint that Simmons's modification had fundamentally changed the Corsair's behavior. Normally, the 2800 engine started with a characteristic roar that built quickly as the massive radial came up to idle speed. But with the steeper propeller pitch, the startup was noticeably smoother, the engine labouring slightly against the increased load. Guyton advanced the throttle carefully during taxi operations, monitoring engine instruments for any signs of excessive stress or unusual behaviour. The takeoff run provided immediate and dramatic evidence that Simmons's intuition had been correct. Where standard Corsairs required nearly 3,000 feet of runway to achieve safe flying speed, the modified aircraft lifted off after barely 2,000 feet. More significantly, the violent torque reaction that normally required aggressive rudder input during takeoff was noticeably reduced. The steeper propeller pitch was converting engine power into forward thrust rather than rotational force, exactly as Simmons had predicted. Guyton's voice crackled over the radio as he climbed away from Stratford's runway, his Texas drawl unable to completely hide his excitement. "Tower, this is Test 47. Aircraft is climbing like nothing I've ever seen. Rate of climb is exceeding 4,000 feet per minute at sea-level power settings. Request permission to continue climbing, to evaluate performance at altitude." From his position beside the runway, Simmons watched the Corsair's climb with growing satisfaction. The aircraft was punching through altitude bands that normally required several minutes of laboured ascent, its massive propeller converting every ounce of the 2800's power into vertical performance. The steep pitch angle that every engineer had dismissed as dangerous was proving to be exactly what the Corsair needed to unlock its true potential. The test flight lasted 45 minutes, with Guyton systematically evaluating the modified aircraft's performance across its entire flight envelope. At 5,000 feet, the Corsair maintained climb rates exceeding 3,500 feet per minute, performance that matched or exceeded the legendary Supermarine Spitfire. At 10,000 feet, where thin air normally began robbing piston fighters of their climbing power, the modified Corsair still managed nearly 3,000 feet per minute, rates that seemed impossible for an aircraft weighing nearly 12,000 pounds fully loaded. More importantly, the handling characteristics that had made the Corsair dangerous during carrier operations showed dramatic improvement. The reduced torque reaction made the aircraft easier to control during high-power operations, while the improved thrust efficiency actually enhanced low-speed handling by providing better propeller response during critical phases of flight. Guyton performed several simulated carrier approaches during the flight, noting that the modified propeller configuration made the Corsair noticeably more predictable during the challenging transition from level flight to landing configuration. When Guyton taxied back to the ramp after landing, his normally reserved demeanor had given way to obvious enthusiasm. "Walter, I don't know how you figured this out, but you just solved every performance problem the Corsair has. This aircraft climbs like a rocket and handles better than any fighter I've flown. We need to get this modification into production immediately." But even as excitement built around Simmons's achievement, institutional resistance from Hamilton Standard threatened to derail the entire program. Arthur Holbrook, reviewing Guyton's flight test data back in Connecticut, remained convinced that the steeper pitch angles would cause long-term reliability problems, even if initial flights showed improved performance. His concerns were not entirely unfounded. Increased propeller pitch created higher loads on engine components, potentially accelerating wear and reducing operational lifespans. More critically, the steeper angles required more precise manufacturing tolerances to prevent vibration issues that could lead to catastrophic failures during sustained high-power operations. The confrontation came during a tense meeting at Vought headquarters on March 18th, where Hamilton Standard representatives argued forcefully against implementing Simmons's modification across the production line. Holbrook presented detailed calculations showing that the increased pitch angles would reduce propeller service life by nearly 30%, while creating stress concentrations in the reduction gearbox that could lead to mechanical failures during combat operations. "Gentlemen," Holbrook concluded, his voice carrying the weight of decades of propeller engineering experience, "I understand the appeal of improved performance, but we cannot sacrifice reliability for speed. The current pitch settings represent the best balance between performance and longevity. Simmons's modification may work for a few test flights, but it will not survive the sustained operational demands of combat service." Commander Blackburn listened to Hamilton Standard's objections with growing impatience. Finally, he interrupted Holbrook's technical presentation with a question that cut through the engineering debate. "Mr. Holbrook, how many pilots has the Corsair killed during testing and training operations?" The question hung in the air like an accusation. Everyone in the room knew the answer. 14 pilots had died in fire, Corsair accidents since the program began, most during takeoff and landing operations, where the aircraft's poor handling characteristics had proved fatal. Hamilton Standard's conservative pitch settings had not prevented those deaths. The Navy's decision came swiftly. Vice Admiral John McCain, commanding the Bureau of Aeronautics, reviewed the test data and authorized immediate implementation of Simmons's modification across all Corsair production. The order specifically overruled Hamilton Standard's objections, noting that improved handling characteristics and climb performance represented critical operational advantages that outweighed theoretical concerns about component longevity. Production changes began in early April, with machinists across Vaught's facility working to manufacture the modified pitch control linkages that Simmons had designed. The work required retraining entire production teams who had spent months learning Hamilton Standard's installation procedures. More challenging, it demanded manufacturing precision that pushed the limits of wartime production capabilities, with each propeller assembly requiring individual adjustment to ensure proper blade angles and stress distributions. The first production, Corsairs equipped with Simmons's steep pitch modification, rolled off Vaught's assembly line in May of 1943, bound for Marine Corps squadrons preparing for combat operations in the Solomon Islands. The aircraft bore standard markings and identification numbers that gave no hint of the revolutionary propeller configuration hidden beneath their cowlings. Only the pilots who would fly these machines into combat would discover how profoundly one machinist's reckless idea had transformed America's most troubled fighter into something extraordinary. The morning of August 13th, 1943, brought clear skies over Guadalcanal as Marine Corps Squadron VMF 124 prepared for its first combat mission, flying the new production, Corsairs. Major Gregory Boyington, The legendary Pappy Boyington, who would later command the famous Black Sheep Squadron, stood beside his aircraft, conducting his pre-flight inspection with the methodical care that had kept him alive through 3 years of aerial combat. The Corsair was new to his squadron, replacing tired Fiat Wildcats that had served well but lacked the performance necessary to dominate Japanese fighters. Boyington had heard rumours about the modified Corsairs and their exceptional climbing performance, but like most combat veterans, he reserved judgment until he could evaluate the aircraft under actual fighting conditions. The Pacific Theatre had seen too many promising aircraft designs that failed when exposed to the brutal realities of sustained combat operations. Weight savings that looked impressive in engineering reports often proved meaningless when aircraft accumulated battle damage and field modifications. Performance advantages demonstrated during carefully controlled test flights frequently disappeared when pilots were exhausted, aircraft were poorly maintained, and combat demanded maneuvers that exceeded design specifications. The mission briefing that morning had been straightforward. VMF 124 would provide high-altitude escort for Navy dive bombers attacking Japanese shipping in the slot. The narrow passage through the Solomon Islands, where Tokyo Express supply runs, kept enemy garrisons alive, despite Allied air superiority. Intelligence reports indicated that Japanese fighter squadrons operating from Rabaul had recently received reinforcements, including some of the Imperial Navy's most experienced pilots, transferred from carrier units that no longer had ships to operate from. Lieutenant Robert Hansen, flying as Boyington's wingman, was one of the few pilots in VMF 124 who had previous experience with the modified Corsairs during training operations in California. The 23-year-old from Lucknow, India, had immediately grasped how the steep propeller pitch transformed the Corsair's tactical capabilities. During pre-flight briefing, he had emphasized to less experienced squadron mates that the climb rate advantage would allow them to control every engagement, dictating when and where combat occurred. The Corsairs launched from Henderson Field at 0830 hours, their massive R2800 engines producing thunder that echoed across the coconut groves surrounding the runway. Boyington advanced his throttle smoothly, feeling the aircraft accelerate with authority that exceeded anything he had experienced in Wildcats or even the vaunted Pfierzig Warhawks he had flown with the Flying Tigers in China. The takeoff roll consumed barely half of Henderson Field's coral runway, and the Corsair lifted off with an eagerness that immediately distinguished it from every other fighter Boyington had flown. The climb to altitude provided the first combat demonstration of Simmons's modification. Standard operational procedure called for fighter escorts to reach 20,000 feet before rendezvousing with bomber formations, a climb that typically required 15 to 20 minutes and consumed substantial fuel. But Boyington's Corsair reached 20,000 feet in less than 5 minutes, its steep-pitched propeller converting engine power into vertical performance with efficiency that seemed to defy basic physics. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Major Robert Gaylor, leading the bomber formation, watched in amazement as Boyington's fighters climbed above his Douglas SBD Dauntless dive bombers with time to spare before the rendezvous point. Radio chatter among the bomber crews reflected their surprise at seeing escort fighters arrive on station early rather than racing to catch up at the last minute. The psychological impact of this seemingly small advantage was significant. Pilots who weren't exhausted from hard climbing had more situational awareness and better judgment during the critical moments when combat began. The first contact with Japanese fighters came at 22,000 feet as VMF 124 approached the target area. Boyington spotted the distinctive silhouettes of Mitsubishi Arsex M0 fighters climbing to intercept the American formation. Standard Japanese tactics called for their fighters to climb above Allied aircraft and attack from superior altitude, using the Zero's legendary agility to compensate for inferior firepower and armor protection. But today, the tactical situation was reversed. Boyington's Corsairs held a 3,000-foot altitude advantage over the climbing Zeros, a disparity that would have been impossible with any previous American fighter. The Japanese pilots, accustomed to controlling engagements through superior positioning, found themselves looking up at enemy fighters that had outclimbed them, despite starting lower and carrying heavier loads. The psychological impact was immediate and profound, forcing Japanese pilots to fight defensively before combat even began. Hansen, following Boyington's lead, rolled his Corsair into a diving attack that exploited every advantage the steep propeller pitch provided. The aircraft accelerated through the dive with tremendous authority, its propeller efficiently converting gravitational potential energy into devastating attack speed. At 400 miles per hour, with altitude advantage and approaching speed that exceeded anything Japanese pilots had encountered, Hansen's attack was essentially unopposed until his 650 caliber machine guns opened fire at 200 yards range. The Zero he targeted attempted a defensive brake turn, pulling hard to evade the diving Corsair. But Hansen's aircraft responded to control inputs with precision that allowed him to track the turning target throughout the engagement. The steep propeller pitch provided not just climb advantage, but superior thrust response during combat maneuvering, allowing the Corsair to maintain energy levels that would have been impossible with standard pitch settings. His sustained burst walked across the Zero's wing root and engine cowling, creating the characteristic flash of exploding ammunition and fuel that marked a fatal hit. The dogfight that followed demonstrated conclusively how Simmons's modification had transformed the Corsair from troubled developmental aircraft into dominant fighter. Where previous American fighters had struggled to maintain energy during sustained maneuvering, the modified Corsairs could match zero-turning performance while retaining the ability to accelerate away from unfavorable engagements. The steep propeller pitch meant that pilots could vary power settings aggressively without experiencing the torque control problems that had made the Corsair dangerous during high-power operations. Boyington himself engaged 3 Zeros during the 20-minute battle, destroying 2 and damaging the third badly enough that it trailed smoke as it fled toward Rabaul. His combat report, filed that evening at Henderson Field, noted specifically how the Corsair's climbing performance had determined the outcome of the engagement before combat even began. The Japanese never had a chance to establish favorable positioning. We climbed above them, dove on them, and they couldn't do anything about it. The success of VMF 124's first combat mission with modified Corsairs created immediate demand throughout Marine Corps aviation for the steep pitch configuration. Squadron commanders, who had been skeptical about the Corsair's carrier suitability, now requested the aircraft specifically for its climbing performance and improved handling characteristics. Within weeks, production Corsairs equipped with Simmons's modification were arriving at Marine Corps airfields across the Solomon Islands and New Hebrides, where they began replacing older fighters that couldn't match their combination of firepower, range, and vertical performance. But the modification's impact extended far beyond Marine Corps squadrons. Navy carrier air groups, which had rejected the Corsair as too dangerous for shipboard operations, began reconsidering that assessment as combat reports documented how the steep propeller pitch had solved the handling problems that made the aircraft unsuitable for carriers. Lieutenant Commander Thomas Blackburn, whose critical evaluation had nearly ended the Corsair program, now found himself advocating for modified Corsairs to equip Navy fighter squadrons. The transformation came during the Battle of the Philippine Sea in June of 1944, when Navy carrier squadrons finally deployed Corsairs equipped with Simmons's steep propeller pitch in the largest carrier battle of the Pacific War. Commander David McCampbell, leading Air Group 15 from the USS Essex, flew a modified Corsair during the engagement that would become known as the Great Marianas Turkey Shoot. His aircraft climbed to intercept altitude faster than any carrier fighter in history, allowing American pilots to position above incoming Japanese strikes before enemy aircraft could reach their bombing altitudes. The tactical advantage proved decisive. McCampbell's Corsairs destroyed 37 Japanese aircraft during the day-long battle, while losing only 3 of their own, a kill ratio that would have been impossible without the altitude superiority that Simmons's modification provided. More significantly, the Corsairs demonstrated that they could operate from carriers as effectively as any Navy fighter, finally vindicating the aircraft design that had nearly been abandoned 2 years earlier. Walter Simmons learned of the Philippine Sea results while working his normal shift at Vaught's Stratford facility, manufacturing propeller components for the hundreds of Corsairs now rolling off production lines. The news arrived via a telegram from Commander Blackburn, who had witnessed the battle from the Essex and understood how completely one machinist's intuition had reshaped naval aviation. Your modification saved American lives today and helped win the biggest carrier battle of the war. Thank you for refusing to accept conventional wisdom. The vindication was professional rather than financial. Simmons received no bonus or special recognition from Vought management, no promotion beyond his position as chief machinist, no public acknowledgement of his role in transforming the Corsair program. Wartime production schedules left little room for celebration, and the institutional culture of 1940s aviation gave credit to engineers and test pilots rather than factory machinists. But Simmons understood that his contribution had been meaningful in ways that transcended personal recognition. The steep propeller pitch that every engineer had dismissed as reckless had become the standard configuration for every Corsair produced for the remainder of the war. More than 12,000 F4U aircraft would eventually be manufactured, each equipped with the modification that Simmons had developed through careful observation and mechanical intuition. Those aircraft would serve in every major campaign of the Pacific War, from the Solomon Islands through Iwo Jima and Okinawa, providing close air support for Marines assaulting fortified Japanese positions and air superiority that allowed American forces to operate without fear of enemy air attack. The technical legacy of Simmons's work extended far beyond the immediate impact on Corsair performance. Propeller engineers at Hamilton Standard and Curtiss-Wright, initially resistant to the steep pitch concept, began incorporating similar principles into designs for other high-powered fighters. The recognition that aggressive propeller pitch could improve handling characteristics while enhancing performance challenged fundamental assumptions about the trade-offs between safety and efficiency that had guided propeller design since the 1920s. Lieutenant Robert Hansen continued flying combat missions with VMF 124 and later VMF 215, using the climbing advantage that Simmons's modification provided to become one of the Marine Corps' leading aces, with 25 confirmed kills before his death in February of 1944. His tactical approach, exploiting altitude superiority to control every engagement, became doctrine for Corsair squadrons throughout the Pacific theater. The steep propeller pitch that enabled this tactical revolution was so fundamental to the Corsair's effectiveness that most pilots never questioned or even noticed the modification that made their aircraft exceptional. Major Gregory Boyington's career with the Black Sheep Squadron demonstrated how the modified Corsair's capabilities enabled aggressive tactics that would have been suicidal in earlier fighters. Boyington's 28 confirmed kills were achieved primarily through combat maneuvers that exploited the Corsair's ability to climb rapidly, engage enemy aircraft from advantageous positions, and disengage when tactical situations became unfavorable. The flexibility that Simmons's steep pitch provided allowed experienced pilots like Boyington to survive encounters that killed less skilled aviators flying inferior aircraft. The modification's impact on pilot survival rates was quantifiable and significant. Marine Corps aviation statistics showed that Corsair squadrons equipped with steep-pitch propellers experienced casualty rates nearly 40% lower than units flying earlier fighter types. The improved handling characteristics reduced accidents during training and routine operations, while the superior climbing performance gave combat pilots advantages that translated directly into better survival odds during aerial engagements. The lives saved by Simmons's work numbered in the hundreds, though precise. Accounting proved impossible given the chaotic nature of wartime record-keeping. The war's end, in August of 1945, brought unexpected challenges for Walter Simmons and thousands of other skilled machinists whose expertise had been essential to wartime production. Vaught's Stratford facility began laying off workers as military contracts were cancelled and production shifted from fighters to civilian aircraft. Simmons, at 54 years old with 3 decades of specialized experience, found himself competing with younger workers for positions in an aerospace industry that was rapidly transitioning from wartime expansion to peacetime contraction. The irony was bitter. The man whose modification had helped win the Pacific Air War was deemed too old and too specialized for the jet age that was transforming aviation. Turbojet engines were replacing piston power plants across military aviation, making propeller expertise increasingly obsolete. The careful machining skills that Simmons had developed over 30 years seemed suddenly irrelevant in an industry focused on high-temperature metallurgy and supersonic aerodynamics. Simmons found employment at a small machine shop in Bridgeport, Connecticut, manufacturing industrial components far removed from the aerospace applications that had defined his career. The work was steady but unexciting, requiring the same precision he had always delivered, but lacking the sense of purpose that came from knowing his contributions mattered to something larger than quarterly production quotas. Like thousands of other wartime workers, Simmons discovered that the skills and dedication that made him valuable during crisis became liabilities during peace. The Corsair itself experienced a more gradual obsolescence. Navy and Marine Corps squadrons continued flying 4U variants well into the 1950s, with the aircraft serving in combat roles during the Korean War. The steep propeller pitch that Simmons had developed proved equally effective in the close air support mission, where rapid climb performance allowed Corsairs to respond quickly to requests from ground forces. Marine Corps pilots flying combat missions over Korea in 1951 would have recognized the lineage connecting their aircraft's capabilities to modifications, developed 8 years earlier by a machinist they had never heard of. The Korean War deployment revealed unexpected durability in Simmons's design. Hamilton Standard's predictions about reduced component life had proven overly conservative. Corsairs, equipped with steep-pitch propellers, demonstrated reliability that matched or exceeded standard configurations, suggesting that the increased loads were within acceptable margins for properly maintained aircraft. The modification that Arthur Holbrook had warned would cause premature failures had instead become a proven configuration that survived years of hard operational use. Lieutenant Colonel Gregory Boyington, released from Japanese prisoner of war camps at war's end, and eventually promoted to colonel in the Marine Corps Reserve, never knew the name Walter Simmons or understood the origins of the propeller configuration that had made his combat success possible. In his post-war memoirs, Boyington praised the Corsair's climbing performance without recognizing that those capabilities resulted from a single machinist's refusal to accept engineering limitations. The disconnect between tactical effectiveness and technical innovation was characteristic of military aviation, where pilots experienced results without understanding the development processes that created their advantages. Commander Thomas Blackburn, retiring from naval service in 1946, carried with him a full understanding of how close the Corsair program had come to cancellation and how narrowly institutional resistance had been overcome. His post-war correspondence with aviation historians emphasized the importance of remaining open to unconventional solutions, particularly when established approaches were producing unsatisfactory results. Blackburn specifically cited Simmons's propeller modification as an example of how practical innovation often came from unexpected sources rather than through formal engineering channels. The broader aerospace industry gradually absorbed the lessons that Simmons's work demonstrated. Propeller designers recognized that aggressive pitch angles could improve performance across a wider range of aircraft types than previously believed. Helicopter manufacturers adapted similar principles to rotor blade design, discovering that steeper pitch angles improved lifting efficiency during the critical transition from hover to forward flight. Even wind turbine engineers, decades later, would apply related concepts to improve electrical generation efficiency by optimizing blade angles for varying wind conditions. Rex Beisel, the Corsair's chief designer, acknowledged in a 1952 interview that the steep propeller pitch modification had been essential to the aircraft's operational success. Without that change, the Corsair would have remained a troubled developmental aircraft, unsuitable for carrier operations or intensive combat use. The admission came reluctantly from an engineer who had initially dismissed Simmons's proposal as mechanically unsound, but Beisel's honesty reflected growing recognition within the aerospace community that innovation often required challenging established expertise. The last operational Corsairs retired from active military service in 1965, when Honduran Air Force squadrons finally replaced their aging 4U variants with jet-powered successors. By that time, the specific technical modifications that had made the Corsair effective had been largely forgotten outside specialized aerospace history circles. The steep propeller pitch that Walter Simmons had developed was simply considered part of the aircraft's standard configuration, its origins lost in the compressed timeline of wartime development and production. Simmons himself never achieved the public recognition that some of his contemporaries received for their wartime contributions. The engineers who designed aircraft systems, the test pilots who flew experimental modifications, the military commanders who deployed new weapons, all received medals, promotions, and historical acknowledgement. But machinists whose hands-on expertise solved critical problems remained largely anonymous, their contributions recorded only in technical documentation that few people outside aerospace engineering circles ever examined. Walter Simmons died in 1971 at the age of 80, having spent his final years in quiet retirement, far removed from the aircraft industry that had defined his working life. His obituary in the Bridgeport Post made no mention of the Corsair program or the propeller modification that had helped win the Pacific War. The few who attended his funeral were neighbors and family members who knew him as a skilled craftsman but had no understanding of his historical significance. The man who had unlocked the Corsair's potential died as anonymously as he had lived, leaving behind no published accounts of his work and no official recognition of his contributions. The rediscovery of Simmons's role came decades later, through careful archival research by aviation historians investigating the Corsair's developmental history. Production records from Vaught's Stratford facility contained references to Machinist-initiated modifications to propeller pitch control systems in March of 1943. Flight test reports noted dramatic performance improvements following implementation of steeper pitch angles. The documentary trail eventually led researchers to Walter Simmons, identifying him as the source of the modification that transformed the Corsair program. The historical irony was profound. One of the most significant technical innovations of World War II, naval aviation, had been developed not by university-trained engineers or military research establishments, but by a working machinist whose 3 decades of hands-on experience gave him insights that formal technical education had missed. Simmons's contribution challenged comfortable assumptions about where innovation originated and who deserved credit for transforming military capabilities during wartime. Modern propeller design still reflects principles that Simmons demonstrated through his Corsair modification. The recognition that aggressive pitch angles can improve both performance and handling characteristics has become foundational knowledge taught in aerospace engineering programs. Variable pitch propeller systems used on everything from regional turboprop aircraft to military cargo planes incorporate optimization strategies that trace intellectual lineage back to the steep pitch configuration that one machinist installed on a troubled fighter in 1943. The Vought Corsair itself achieved legendary status in aviation history, remembered as one of World War II's most effective fighters, and the aircraft that gave Marine Corps pilots air superiority throughout the Pacific campaigns. That reputation rested fundamentally on capabilities that Walter Simmons's modification provided. The climbing performance, improved handling characteristics, and tactical flexibility that distinguished the Corsair from contemporaries. Without the steep propeller pitch, the 4U would likely be remembered as another promising design that failed to achieve its potential, rather than as an iconic weapon that helped win the war. The final assessment of Simmons's achievement requires understanding both what he accomplished and what his success revealed about innovation during crisis. The steep propeller pitch was not a revolutionary new technology requiring years of research and millions of dollars in development funding. It was a straightforward mechanical adjustment that could have been implemented at any point during the Corsair's troubled development cycle. What made it revolutionary was not technical complexity, but the willingness to question established engineering wisdom and the courage to test solutions that violated accepted safety margins. Lieutenant Robert Hansen, whose tactical brilliance had exploited the climbing advantages that Simmons's modification provided, never knew the name of the man who had made his combat success possible. Hansen's 25 kills represented not just individual pilot skill, but the accumulated advantage of superior technology and tactics. The steep pitch propeller gave him altitude superiority. That altitude superiority gave him tactical control. That tactical control allowed him to survive and prevail in aerial combat, where margins between life and death were measured in seconds and hundreds of feet. The 23-year-old ace died, never understanding that his effectiveness as a fighter pilot depended partly on the technical insights of a 52-year-old machinist working night shifts in a Connecticut factory. The disconnect between innovation and application, between technical development and tactical employment, characterized much of wartime weapons development. Success required contributions from people who would never meet and often never know of each other's existence. By the time aerospace historians finally documented Walter Simmons's role in the Corsair program during the 1990s, everyone directly involved with the original modification had died. Simmons himself, the engineers who had opposed his idea, the test pilots who had validated it, the combat aviators who had exploited it, all had passed without leaving detailed accounts of their experiences. The story survived only through fragmentary documentation in corporate archives and military records that required years of patient research. To reconstruct, the Corsairs that survived the war and found their way into museums and private collections bore no plaques identifying Walter Simmons or explaining how a machinist's reckless idea had transformed their capabilities. Visitors who admired the aircraft's distinctive gull wings and powerful radial engine remained unaware that the propeller configuration they were looking at represented innovation as significant as any engineering breakthrough of Vought. The most important modifications were often the least visible, hidden in technical specifications and mechanical adjustments that casual observers never noticed. The aerospace industry's evolution, from piston engines to jets, and eventually to computer-controlled systems, obscured the human expertise that had once been central to aircraft development. Modern engineers designing propeller systems for turboprop aircraft used sophisticated computational models and wind tunnel testing to optimize blade configurations. Those tools would have amazed Walter Simmons, who had relied on observation, experience, and mechanical intuition to solve problems that conventional engineering approaches had failed to address. Yet, for all the technological advancement, certain fundamental principles remained constant. The recognition that established expertise could be wrong, that unconventional solutions deserved consideration, that practical experience sometimes revealed insights missed by theoretical analysis. These lessons that Simmons demonstrated in 1943 remained relevant generations later. Innovation still required courage to challenge accepted wisdom and willingness to test ideas that violated established norms. The Corsairs' service in the Korean War provided a final validation of Simmons's work under conditions he could never have anticipated. Marine Corps pilots flying close air support missions over mountainous Korean terrain discovered that the steep propeller pitch gave them climbing, a performance essential for operating from primitive airfields at varying elevations. The modification developed to solve carrier landing problems proved equally valuable in completely different operational environment, demonstrating how effective technical solutions often had applications far beyond their original intended purpose. Major General Vernon McGee, commanding Marine Corps aviation in Korea, wrote in his operational report that Corsair climbing performance had been critical to mission success in terrain where altitude capability determined whether aircraft could safely operate. The steep propeller pitch that enabled those climbs had become so standard that McGee and his pilots took it for granted, never questioning the configuration or understanding its origins. The best technology became invisible, functioning so reliably that users forgot it represented human ingenuity rather than natural law. The final Corsair production aircraft rolled off Vaught's assembly line in December of 1952, ending a production run that spanned nearly a decade and produced more than 12,000 examples. Every one of those aircraft incorporated the steep propeller pitch that Walter Simmons had developed, making his modification one of the most widely implemented technical innovations of mid-century aviation. The scope of impact was staggering when measured by the number of aircraft affected and the combat effectiveness those aircraft achieved. Yet Simmons's name appeared nowhere in official Corsair histories published during his lifetime. Vought's corporate documentation credited the aircraft's success to Rex Beisel's design genius, to test pilots like Boone Guyton, who had validated performance improvements, to Navy commanders who had advocated for the aircraft's operational deployment. The Machinist, whose single modification had transformed the program, remained anonymous, his contribution known only to a handful of engineers who had access to detailed production records. The injustice of that anonymity reflected broader patterns in how technical achievement was recognized and rewarded during the mid-20th century. Formal education, professional credentials, and institutional position determined who received credit for innovation, while practical expertise and hands-on problem-solving went largely unacknowledged. Simmons lacked the engineering degree, the professional status, and the institutional authority that would have made his contribution visible to history. The aerospace engineers who eventually documented Simmons's role did so not to correct historical injustice, but to understand how the Corsair had evolved from troubled developmental aircraft to legendary fighter. Their research revealed that crucial innovations often came from unexpected sources, that institutional resistance could delay implementation of valuable ideas, and that success in weapons development required contributions from people across organizational hierarchies. These lessons informed how modern aerospace programs approached innovation and expertise. The propeller blade angle that had seemed so reckless in 1943 became standard configuration, not just for Corsairs, but for numerous other high-powered piston fighters developed late in World War II, and immediately after. The Grumman Facht F. Bearcat, Republic P-47 Newton Thunderbolt, and North American P-50H Mustang all incorporated steep propeller pitches similar to what Simmons had pioneered, though subsequent engineers arrived at those configurations through formal analysis rather than intuitive mechanical insight. The validation of Simmons's approach came through independent confirmation that his instincts had been correct. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.